Last week in class, we talked a lot about our rules for integration. I wanted to do a few more practice ones from the packet before we get into 4.2. So let's practice using things such as the reverse power rule and the rules for natural logs, exponentials, and so forth to solve antiderivatives. And just to recap quickly, main message from last class is that we use the integral symbol to denote an antiderivative. Basically, we are trying to find what function has this particular derivative. And the differential indicates with respect to x in this particular case. We'll talk more about the meaning of this symbol very, very soon. But anyways, when it comes to a power function, remember that the reverse power rule is that we want to add 1 to the power and then afterwards drop the reciprocal, because we're trying to counteract the way the derivative works, which is when you're taking a derivative of a power function, you drop the power, then subtract 1. So this is the exact opposite in the opposite order. Add 1, then drop, instead of drop, then subtract. So if we want to find the antiderivative of x to the 7th, we would need to add 1, so that would be x to the 8th. And then we would need to drop the reciprocal, 1/8. Or you can think about it as multiplying by the reciprocal is what I mean by drop, or dividing by the coefficient. Same difference, right? Whether I multiply by 1/8 or divide by 8. And as I emphasize in class, every indefinite integral, we always need to add plus c to the end, because any function and an antiderivative of anything could involve a constant, and we are not really sure. And also in the next video or two, I want to talk a little bit about how do you solve for c if you are able to, and what does that look like. But anyways, this would be our antiderivative. And again, as I was emphasizing in class, you can always check by taking the derivative of this. Derivative of x to the 8th is 8x to the 7th. And 8 would multiply by 1/8 to cancel, and that would leave us with x to the 7th. It checks out. And the derivative of a constant is 0. And remember, we want to focus on the interior of that, and the dx and the integral symbol, those do have meaning, but in terms of finding antiderivative, we're just focused on what's in between those two things always. So doing a few more, let's say I wanted to know the antiderivative of the square root of x, but just like with the power rule before, if I know how to rewrite my function as a fraction, I could rewrite the square root of x as x to the 1/2, and now I could solve the antiderivative by reverse power rule. Again, which I need to add first, so 1/2 plus 1 is 3/2, and then drop the reciprocal 2/3. Add c, and we are done with our antiderivative. So say we had x to the 0.3, and we wanted to know what is the antiderivative. We would add 1, so that'd be x to the 1.3, and then we would drop the reciprocal. Another way you could write it is just x to the 1.3 over 1.3, or you could figure out, okay, what is that fraction, and so forth. But, however you want to write it, either as 1/8 or, 1 over 1.3, or just the power function, add 1, divide by 1.3, same difference. And again, as always, don't forget when you're solving an indefinite integral, when there are no numbers on the symbol, we'll talk about what that means pretty soon as well in class next week, then you don't need plus c. Anyways, that more to come on that. And then if we have, say, division by x, again, we can't apply the reverse power rule here because it needs to be on the top in order for it to work properly. But we could always use our rules for powers. 1 over x to the 4th is the same as x to the -4th. And then after we change it to a power function in its normal form, we can then apply the power rule, the reverse power rule, as I usually call it that, because to distinguish it from the rule for finding a derivative. So I would add 1, and again drop the reciprocal, -1/3, plus c, and there we'd have it. Or again, usually we'd like to write this as -1 over 3x cubed plus c. Return it to its form. Since it was presented in a form involving division, we could leave it that way. And same with this one, I could write this as x, the square root of x cubed, but at the end of the day, same equivalency. And using some of these other rules like the e rule, the log rule, or the constant rule. Another basic one is when I have the antiderivative of a constant, remember that the derivative of a constant is 0. But the antiderivative, it should involve x. And an easy way to remember this is actually another kind of basic antiderivative rule you can remember is the antiderivative of dx is always just x. And there's some logical reasoning behind this. But it's kind of like, well, if you're taking the antiderivative of a derivative, which that's not exactly what a differential means, it should return you with just a variable x. But but if you put a 1 in here, this can also help you think about that, because the antiderivative of 1 is just x, because the derivative of x is 1. So if you kind of leave nothing in there, that's what dx is by itself. Again, we'll talk more about the meaning of dx in the integral symbol soon. But yeah, that's like a little factoid you can remember. Or obviously just kind of remembering with polynomials, even with constants and numbers, they always should be gaining a degree, like they should be going up by 1. So this currently has no x's, it should gain an x in its antiderivative. So the antiderivative is just negative 50x plus c, and that is it. Again, needing plus c as always. Because the derivative of negative 50x, again, the derivative of x is 1. The antiderivative of 1 is x. And that's, again, kind of another one of those basic properties you can remember. Or, as the rule was the constant rule, the antiderivative of a constant is kx plus c, of course. Because a derivative tells us the slope. An antiderivative function actually is kind of like what function has this slope. It's kind of it's like a backwards question because it's a backwards idea. And then the antiderivative of e to the 5x, if we were to just use the rule, we could write this as, well, this would be 1/5 e to the 5x plus c. And again, remember that, there's a big warning up here, which is the chain rule does not work the same with integration. And the same is actually true with the power rule and the quotient rule. A lot of those rules that we learn for solving derivatives do not work at all with integration. And there's a reason why. It's because they don't undo themselves in quite as simple as a way. There are strategies and techniques for trying to reverse those processes, which we call integration by parts, use substitution, and these are algebraic techniques that we're going to be working on in the next couple weeks. After we talk, we're going to be spending a good couple weeks on the idea of integration. What does it do? What does it mean? Because that is ultimately more important. But anyways, what was my point here? Remember that if you're differentiating e to the 5x, you should get a 5 that drops out. So it would be 5e to the 5x, and that's why we need a 1/5 here. So an easy way to remember this one is with e to the ax, it works fairly similarly to a linear function where you have either fraction dropping out, but it's sort of similar to the reverse power rule where I need to drop that fraction out if it's in this particular structure. And then another one that's a little tricky is, like, say you have the integral of 0. If you wondered what is that, what would that do? The antiderivative of 0. But if you recall that any constant has a derivative of 0. So actually, the integral of nothing is actually quite a simple answer. It would just be c, because if you were to think about it using the constant rule, 0 is technically a constant. The antiderivative of a constant with respect to x is equal to the constant times x plus c. So in the case of 0, we'd have 0 times x plus c. Well, of course, 0 times x is nothing. Or again, the function that has no slope is a constant function without any x. So essentially, it can't have x when it is 0. And that leaves us with just c, because the derivative of c is 0. And this kind of helps you, this helps me remember or think about why do I need c when I'm doing an antiderivative. Because even if I had absolutely nothing, the antiderivative of even nothing is something. Unlike a derivative, right? The derivative of nothing is nothing, ddx of 0. Even a ddx of constant is 0. So derivatives kind of simplify things. Integrals kind of complexify. They make it a little bit more complicated. Even 0 turns into something, hypothetically. Again, we don't know what. It could be any number that has antiderivative of 0, which is why we refer to antiderivatives as a family of functions, because it could be, it could be 1/8 x to the 8th plus 7, or 1/8 x to the 8th plus 100. We don't really know, but that c just represents any number, which it could be.